Welcome to this video on the potential due to a point charge, and what we're going to do in this video is look at employing the definition that we came up with in the last video in order to actually put it to use in a field that's not constant. So just as a reminder, the definition we came up with in the last video was potential difference is going to be equal to the negative integral from some initial position to some final position, whatever these are, of the electric field dot ds, the tiny little path that we will take. Now, what I'm going to do is I'm going to make an electric field here with the help of a positive source charge, and I'm going to draw some field lines to establish and to remind you that the electric field is not constant, and the electric field at any point r away from this source charge would be given with the expression 1 over 4 pi epsilon naught times q over r squared. Now, what we're going to say is we want to move a little positive test charge from this position, which I'm going to label big R, all the way out to the point of infinity. So really, really far away. And it's actually pretty clever to do this, and this is the way this idea is structured, because what that does then, it says that the final potential is going to be 0 because that's the potential that's at infinity, 0 volts, of course. And the initial voltage, I'm going to label just V because that will be just a little bit easier to have to write all the time, seeing as this one is just 0. And what I'm going to do here now is go from R all the way to infinity to calculate an expression for the voltage at the point R. So you can see that by making this point 0, we get an expression for just voltage at that particular point because it's in reference to infinity, which is just 0. So let's go ahead and write this out again. So I'll do Vf is 0 minus Vi, which I'm leaving in as V, is equal to negative E. And instead of having to write the dot product now, because just as a reminder, the delta x, right, the displacement and the force QE, they are at 0 degrees to one another, and of course the cosine of 0 degrees is just 1, so that gets rid of that. But I am going to change ds to dr because I'm dealing with radial displacement here. And remember, I'm going from position R all the way to infinity. Now what I'm going to do is substitute in this expression in for E. So let's go ahead and do that. So we have 1 over 4 pi epsilon naught times q over r squared dr. Now there's a whole lot of constant stuff over here, so I guess let's go ahead and pull all of that out. Q over 4 pi epsilon naught integral from r to infinity of 1 over r squared. Sorry, that should be a little r. Let's go ahead and get that right. dr. Okay, so once I've actually done the integration here, what ends up happening is, keep in mind here, this negative sign and this negative sign are going to factor out now when I do my calculation. And so what I'm going to be left with at this point is, let me switch the color here so we can see it, q over 4 pi epsilon naught, and then the integration is going to leave me with 1 over r, and I'm going to evaluate this from r to infinity. Now, of course, at infinity, this is all 0, right? So when I do 0 minus all of this at r, I come back to a negative again. So you see this negative went away, but it's come back again now, and the expression is equal to 1 over 4 pi epsilon naught times q over, and in this case, big R. So basically what that says then is that the potential at R is equal to negative 1 over 4 pi epsilon naught times q over big R. And we can generalize that for the electric potential at any point in a field, not just big R, and we can do that by saying that it's going to be equal to 1 over 4 pi epsilon naught times q over little r. Now keep in mind, I took the negative out of here, and the reason I did is because this was specifically from r to infinity, and that's why the negative came into play. But this, you could do this for different positions, and just recall that this works for a negative charge just as well as it works for the positive charge, but be careful that you remember that you need to plug in the negative sign here. So you can see that whatever the charge is on Q, that will be the charge on V as well. I mean, that will be the sign on V. So the sign negative Q will make V negative, and the sign positive Q will make V positive. Hence, we talk about the places of high potential being positive, the places of low potential being negative. This is a scalar quantity, as we've said before, and so we don't have to worry about any directions, but we do have to worry about keeping the sign on the charge and the potential. So a positively charged particle produces a positive electric potential, and a negatively charged particle produces a negative electric potential. It's pretty straightforward and pretty interesting. In the following videos, what we're going to take a look at is just a few more applications of this, particularly looking at a continuous charge distribution for the electric potential.